Hello. Hello.
Hi Ananya, good evening.
Good evening, sir.
How are you?
I'm good. How are you?
I'm good. You sound tired.
Yes. Oh, school. Just got back.
Okay. Oh, I am rushing you. I'm sorry.
No. Today actually they left us few minutes late,
Oh, okay.
and
That's fine. That's
it
fine.
was like PCM block period we had, so it was
Acha,
hectic.
acha. It's okay. We can always delay by 5-10 minutes. There is always margin for that. There is not an issue. It's
Fine.
important that you're comfortable to start the class. Don't rush into it.
Yes.
Take your 5 minutes. Okay. Anyway, so last time,
Mm-hmm.
what did we do?
You had given homework. Okay. So basically, you said there's one last part of the chapter left, and we were solving numericals. We did that electric flux.
Okay.
And, yeah, through the cube, passing through the cube.
So, yeah.
Continuous charge distribution.
Okay. Yeah. So, did I give you any homework?
Yes, you asked me to solve in the exercise. I did a couple of them. No, also, what I wanted. Oh my god. Okay, what I wanted to ask is, instead of homework, I have holiday for the next 3 days: Friday, Saturday, Sunday, all 3 holidays. Can we take more classes and solve the problems in class itself?
I didn't get you.
Maybe for a week or two. Can I not get homework and we'll solve the problems in class? Because the thing is, practicals, I joined late, right? Very late. So practicals, they finished about 17 experiments in chemistry and about 9 or 10 in physics. So I have to write those and I have to immediately submit.
Okay.
That will take
Not an issue. What we'll do is we'll spend more time in problems initially now, till that time, and then later you can just. So that is designed basically to save your time. But since you're busy, so what we'll do is we'll just, like you said, we'll just take up the classes in questions in the class itself, right?
Yes.
So cool. So have you done the past homework that I gave you? Did you do that?
The exercise that you're given?
Yes.
Yes, in that NCRT I did, and I cross-checked the answer at the back, and I have a doubt in one.
Okay, tell me.
So I have solved 1.10, that is 10.
1.10.
And I have solved 2 more, and the other 2 are doubt. So basically, I tried to solve till 15.
Just a second.
So yeah.
Did you do examples or exercise? Exercise, right? You did
exercise, sir. Okay. Yeah. Examples we actually did in class.
Yes. Which one was your doubt? Now you can tell me.
Yes. Just 1 second. I got that answer wrong. Excuse me. Okay. So 1.6.
Okay. Yeah.
I solve. We have 2 equal forces, two forces or 2 charges. Sorry, charges are 2 coulombs and the other 2 are -5. I found out the force on charge at point 2 due to each charge, and then at the end, I didn't get how to add them.
Okay, like vectorially.
Yeah.
Let's see. This is my square in question, and the location of the charges is also given to us. Their magnitudes are also given, I believe. So this is question 1.6. We're discussing from exercise. So it says that charges are A, B, C, D. Okay. A, B, C, D, and the values are also given. Like A is 2 microcoulomb, and B is -5 microcoulomb, and C is 2 microcoulomb, and D is minus 5 microcoulomb. Okay. And at the center, there is another charge of 1 microcoulomb. That's it. That's the scenario. So here you must have calculated the forces individually for each. So let us say
No, sir, FOA equals OB. I mean, FOA equals OC, and OD is equal to OB. So I calculated 2.
So it should be 0, right?
No, I didn't understand. After I calculate those, okay. So basically, I got, okay. Okay. So once I calculate each force, the net force is equal to FOA plus FOB plus FOC plus FOD, right?
Vector form, not scalar.
Yeah, like vector form, yeah.
Yeah.
Then how do I
Yeah,
add them
so
up?
there are several ways. For example, when there are cases like, here it's absolute total symmetry, you can see the green ones will cancel and the red ones will cancel. So you can say that FOB and FOD cancel each other, and FOA and FOC, since they're equal and opposite forces, right? They're along the same line. So forces you can add or subtract if they are along the same line. You can add and subtract directly. If they are in the same direction also, then you can add. If they are in opposite directions, you can subtract, right? So here we can see the green ones will be equal in magnitude and they are opposite to each other, so they will cancel. And the red ones are equal in magnitude, opposite to each other, they will again cancel. Second thing you could have done here, we don't need to do it because there is symmetry. But if this kind of cancellation is not happening, then we have like couple of things we can do. One thing we can do is we can break the forces. Okay, like I told you, along the x direction and the y direction. That way you have to take
by breaking them, could you solve how to solve like that?
Yeah, that I'll show you.
But okay, here I understood. It's understood because they're equal and they're opposite. So it'll cancel each other.
So net force F should be equal to FOA vector plus FOB vector plus FOC vector and FOD vector. Now the most, I'm not saying shortest or easiest, but most reliable way where you'll get answer for any kind of case is basically just breaking them into x and y axis. This is your x axis and this is your y axis. So what you could do is you could break each of them. For example, FOA is here, so you know that this angle is 45 degrees since this is a square. So this will be cos 45, that will be sin 45. So it will break into components. So one will be here, FOA cos 45, this one is FOA sin 45. So basically let me say that this is FOA by root 2. Okay, and what is the direction for this? This is minus j cap, you can say, and minus I cap. Minus I cap and minus j cap are the directions of the two components. This one is along the negative y, x, and this one is along the negative y. So you could say FOA sine theta minus I cap plus FOA cos theta minus j cap. And you know the value of FOA, so you can actually find the I cap and j cap form of this. Similarly, you do for FOB, that will also be something like FOB by root 2, and then for, so let's see, for B, the x component will be, can you tell me, plus I or minus I for FOB?
For FO?
B.
It's going to be, x is going to be plus, y is going to be minus.
Very good. So basically this is your plus and this is your minus. So what you'll do here is you'll just say plus I cap and then FOB cos theta or sine whatever, same thing, because 45. So you don't need to worry about that. This will be minus. Okay, similarly you can see FOC. Can you tell me for FOC? The x component will be?
Both are positive.
Correct, very good. So that will be I cap and this will be j cap, sorry, FOC by root 2 j cap. This will be your third thing, right? And the last thing will be FOD, and FOD you can write as minus I cap plus j cap, right? So FOD by root 2 minus I cap plus FOD by root 2 plus J cap. Okay, so basically now you can just do this again, but with I cap J cap form. So you will see that F equal to FOA. FOA can be written as FOA by root 2 and minus I cap minus J cap. FOB can be written as FOB by root 2 I cap minus J cap. FOC can be written as FOC by root 2 I cap plus J cap, and FOD can be written as FOD by root 2 minus I cap plus J cap. These are the four forces, and then you know the values of FOA and FOC will be equal. So you can actually take this thing common. Let me call FOA equal to FOC equal to F1, right? FOA equal to FOC equal to F1, and FOB equal to FOD equal to F2. You following me? So here what I'll do is F1 by root 2 minus I cap minus J cap, and then I can also take for FOC plus I cap plus J cap. You can see they will cancel. Similarly, F2 by root 2 will become I cap minus J cap minus I cap plus J cap. So you can again see these are cancelling. So you're getting 0, but you may not have had 0 all the time, right? In that case, you can find the force in the I cap J cap format without them being 0.
Yes.
Yeah. So that you can note it now if you need to.
Yes, I will. Okay, sir.
Okay, next one.
Next one is one. Okay, so 1.7, I wanted to know if you could tell the answer. It's like a theoretical one.
Electrostatic field line is a continuous curve, that is, a field line cannot have sudden breaks. Why? And explain why two field lines never cross each other. So second one, I think you already know. Why two
Yes.
field lines?
Two tangents will be there, like.
Yeah. Similarly, see, electrostatic field line is a continuous curve because whenever there is a charge in between, okay, then it becomes a discontinuous curve, right? Otherwise, the field needs to
Yeah.
flow. Okay, it can't be like, there is a break, sudden break, because field is a continuous entity, right? Physical entity. It's not just a line. It actually exists, right? So electric field can only have breaks when there is a charge present. Okay, like for example, maybe we can say like this is a negative charge. So a field line was coming and it stopped. When there was another charge present here, right? If there is no charge here, then this field line will not stop. It has to go continuously since electric field is a continuous entity. You can see that this is a continuous curve, right? And it will only stop only when charge is present. So when charge is absent, in the absence of charge, electric field needs to flow continuously, right?
Yes.
So maybe you could write that electric field is a continuous entity and electric field lines are supposed to represent electric field itself. So in the absence of charge, it will not break. There will be no sudden break. But if there is a charge present, in that condition only, there is a break in the electric field line, right?
Okay, fine. I think I got it, yeah. One second, I'll just write it down in words. Hello?
Yes, yes.
Yeah, I'll just write it down in words.
Okay. Take your time.
Okay, sir.
Okay. Next one.
Next one, that's done. One second. This is okay. Yeah, ninth one.
Ninth one is asking, a system has two charges, QA, QB, located at points A and B, respectively. What are the total charge in electric dipole moment of the system? Okay. So total charge, though, you can see it will be zero, right? Because one is positive charge and the other is negative. So total charge QA plus QB will be zero, right?
Oh, yeah.
I hope you can see that.
Oh, okay.
One is positive and the other is, anyway, for a dipole, you know, the net charge has to be 0.
Yeah.
Where
Okay. I got confused. Like they gave these dimensions, and then I thought, okay.
oh, the locations don't matter, right? The total charge
Yeah.
is what matters. Okay, so that's one thing. And dipole moment. Dipole moment formula is what? See, the locations are given here. Okay, so let's say that this is located at -15. Other two coordinates are anyway 0. So I'm just drawing one axis here. And the other one is located at +15. Okay.
Yes, that's right.
So they are asking what are the total charge and dipole moment. Dipole moment will be basically just charge into distance between the charges, right? So here charge is given to be minus 2.5 into 10 to the power -7, and the other one is given to be 2.5 into 10 to the power -7. Okay, what is the distance between these two charges? You can see distance is 30 centimeters, right? So if you
Yes.
take it in SI units, that will be 0.3 meters. So 0.3.
Yeah. Yeah. Right.
So then basically dipole moment P will be given by Q into D, D being the distance, 2.5 into 10 to the power -7 into 0.3. This will be your dipole moment in SI units.
Okay. Okay. So also in 1.8, I got one part of the answer right, and the other part of the other part. Okay. So basically, they've asked if they place a charge in between at point O. In
part
question
A, part A.
No, part B.
If a negative charge of magnitude this much is placed at this point, what is the force experienced by the test charge?
Yeah, that I'm getting wrong.
Okay. So when you are at the midpoint, the net electric field will not be 0, right? It won't be 0. I hope you get that, because the electric fields will be in opposite direction, right? So basically, what you're going to get is 1, 2. There are two charges, right? And the charges are of magnitude -3 microcoulomb at 3 microcoulomb.
Okay.
And what is the distance they have given? That is 20
That
centimeters.
is yes, 0.2 meters.
So you can say the distance is 0.2 meters. So that simply, if you try to find at the midpoint, this is the midpoint, you can say that this one is having electric field in this direction towards the charge because it's negative, and the other one have on the same direction because that is positive, and we have to have away from the charge, right?
Yes.
So that's it. They will add E due to positive charge and E due to negative charge should add, even though you can see that one is positive, other is negative, but because electric field is a vector quantity, that's why you can say that the electric fields in this case will add. Such is the configuration of the charges, the way they are placed, right?
Got it.
So what is the value of electric field for any one of these? We can see by symmetry both the values will be equal. So you can tell from anyone.
So for one, it is 2.7 into 10 raised to 6.
Okay, you found that. Great.
Yeah, that is done. That was part A, so I found that.
It turned out right. That with 2, right?
Yeah, that I did.
Then to find the force, you just have to multiply with the test charge, the charge which will experience the force. It's a 1.5 into 10 to the power -9 coulomb. So you have to multiply the electric field, total electric field, with the magnitude of the charge.
God! Oh, so I use the formula K Q1 Q2 by R square again.
Why? Why did you do that?
Oh.
It's okay.
Okay. Yeah. This was actually easy. So doubts, that's it.
Oh, how many you did questions?
I did until 12. So I didn't do the 13th one, but then I don't know because the diagram was there. I saw the 14th one, and I thought I won't get it. I mean, like I tried, but I didn't get it.
So you tried 13th one?
No, 14.
14th one you tried?
Yeah, can we solve that now?
Yeah, sure. Did I give you as homework that question?
Yes, you had said until 24 I can solve. No, 24 I can't solve. Until 23 you said I can do as much as possible.
Okay. So let's so your doubt is 14th basically, right?
Yes. 13th I haven't done yet. Okay. So basically till 12 I've done, and 14th I tried and I didn't get it actually.
No problem. You can try the 13th one later. Okay.
Yes. So this 14th one, there was a similar question in the examples also. That type of problem I'm not able to get it. I don't know why.
Okay, let's see.
Yeah.
So basically you are having a positively charged plate, let us say here. And there's another at the bottom. So here we must understand that what these positive and negative charges will do. Okay, here there are lots of positive charges on this plate. There are lots of negative charges on the other plate. So we know that electric field, or we should know, flows from positive to negative charge. So there will be an electric field from the plus to minus plate. This is the electric field. We are not concerned with the value. As for value, we'll study in the next chapter how to find the electric field for a charged plate.
Okay.
But for now, we can at least say that electric field value we don't know, but direction we know, right?
Yes.
So if there is a charge here, they are saying there are 3 charges, 1, 2, and 3.
Yes.
So 1, 2, and 3 means the first one we can see is deflected in upper direction.
Yeah.
That means the force it experienced was in the upward direction.
Okay.
You understood this?
Understood.
Yeah, because it is deflecting upwards. So this is experiencing force in the upward direction. Second one also you can see, again that is moving upwards. So second one also experiences force in the upward direction. Whereas the third one is moving downwards, deflecting downwards. So definitely it experiences force in the downward direction. That means if the charge is experiencing force in the same direction as the electric field, then it is supposed to be positive. Here the field is downwards. So force experienced downwards only by this charge. So this is a positive charge, whereas the other two experienced in the opposite direction. So these are both, you can say, are negative. So this is more like logic based, right?
Yeah. Okay. So the second one, could you explain again how it is negative? The first and third I understood.
Yeah. Second one is also negative because it's moving upwards, right? It starts from the middle, then it moves upwards. We are only interested in how it will deflect.
Okay, so basically the basic thing, the first we learned that in the chapter, like towards the positive charge, negative and positive attract.
Yes. So here the charges are not affecting each other as they are, they are separately we're discussing, not together.
Yeah. Like 3 different cases.
Yeah.
Got it. Which particle has the highest charge to mass ratio?
Yeah. So charge to mass ratio means we have to write basically if deflection is more, then charge to mass ratio is also more. Why? Because see acceleration. So force is I'll write force first. So force can be written as Q into E. E is constant, whatever it is, for all 3 cases. Now I can say this is mass into acceleration. Force is equal to QE. So acceleration is Q by M into E. Ratio Q by M. If it's more, then acceleration is more. And acceleration is more means doesn't matter the velocity. You're not concerned that speed will change. The direction, okay, the direction will change even much more, right? Like if acceleration,
Yes.
you must have studied in circular motion, that centripetal acceleration is there, and that means if deflection is more, then we'll say that charge to mass ratio is also more. You can see that particle 3 deflected the highest. I mean, it really got deflected
Yes.
by a large amount, and that's why we can
Yeah.
conclude that particle 3 has the highest charge to mass ratio.
Got it.
Great. Your cough is gone, huh? You're fine now, I guess.
Yes. Yes.
Amazing.
Fine. I mean, it's coughing a little here and there, but basically the
Better
cold's gone.
than before, yeah.
Yeah. Yeah. One second, sir. I'll just write this down like in 2, 3 lines.
Sure, please. Go.
Class. Yeah. Yeah. Oh, yeah. So, hello. Sir, just a minute, sir. Could you give me a minute? I'll be back.
No problem. Please go ahead.
Hello?
Yes.
Yes. Charge and present equals QE, MA equals QE, QA is QY. Negative, negative, positive. Okay. Excuse me. Hello? Done, sir.
Okay, next one.
So also, but I have a holiday tomorrow and day after as well.
Okay.
So in case you're free, we can keep an extra class.
In the morning, I believe.
Yes, morning is also okay. At around what time, sir?
Morning I start usually 10 o'clock, something like that, 10 to 12.
Okay. Okay, actually, the chemistry class, I'm taking it in the morning tomorrow from 9 to 11.
Okay, so we can have from 12 to 2, I guess.
12 to 2 is okay?
Yeah, that will also work because my regular classes will obviously start at 3:15 or 3
Okay.
max. So definitely.
Okay, fine. We can keep it from 12 to 2 then.
Okay, I'll just note it down in my calendar.
All right. I'll just tell sir that I'll be taking.
Sure, sure, sure.
Hello?
Yeah, are you done?
Yes, I'm done. Yeah.
Okay. Next, any more doubts do you have?
No, that's it.
Cool. So I think we'll move on to the next topic.
Yes.
The last thing we did earlier, we had some applications of Gauss law remaining. Let me just confirm
Yes.
that. Just a moment. So the last class was held on Tuesday. And yeah, last part of Gauss law remains, and exercise I have given as homework. I
Huh.
think we have already discussed what is Gauss law, and let's check this. Gauss law we discussed. In Gauss law, last thing we discussed was field due to a thin spherical shell. Okay, now we'll talk about thick shell, solid shell basically, and we'll talk about line charge, and then we're going to talk about a sheet. Those are the three things left. Then we'll do some questions.
Oh, sorry, I didn't get you.
No, I'm saying that now we'll do some advanced parts of Gauss law, right?
Okay.
And then we'll just do some questions based on that.
Okay, fine.
So till now we discussed Gauss law, how to apply for point charge. I hope you are revising these things side by side.
Yes, I
For
am.
point charge and also for thin spherical shell. Now we'll see electric field due to a solid sphere. So let us suppose that I'm having a sphere which is charged. So I'm just gonna take a red thing, and this is not just a sphere, it's like it's totally charged. So maybe I'll just go for a yellow one here. Okay. This is a charged sphere. Okay, not like a shell
Yeah.
or something. This is actually having charge everywhere, uniform charge. Okay, so it's better if I write here due to a uniformly charged solid sphere. Because see, if the charge is non-uniform, then we have to do something else. But in CBSE, they will definitely not ask non-uniform one. So only uniformly charged solid sphere. Okay. There are two cases that will come out here. Number one is outside, field at a point
Yeah.
outside. So at point
Mm-hmm.
outside, I'll just take a Gaussian surface, just passing through this point P, like I've done so many times. And then
Yeah.
I'll just take this here. This looks like an egg for some reason. But
Yeah.
yeah, so this is point P is where I'm going to calculate the field. Okay, so here I know that field is supposed to be radial firstly, so it will definitely
Yeah.
be in the outward direction. Okay, and I
Uh-huh.
also know that because of symmetry, field will be same everywhere. So when I apply Gauss law, I can say by Gauss law,
Mm-hmm.
flux E dot ds can be written as Q in by epsilon naught. Are you listening?
Yes.
Okay. So E is constant, so I'm just going to take that outside. That becomes EDS equal to Q in by epsilon naught. And ds integral will be 4. Also, one thing here I should mention, EDS is nothing but integral of EDS. E dot ds is nothing but EDS because field, I'll say electric field and area vector
Mm-hmm.
are parallel
Yes.
at all points on the surface,
Yeah.
like we did earlier also. So that's why we can say that this E dot ds will become simply EDS is
Mm-hmm.
Q in by epsilon naught, and E is constant. So since E is constant or uniform on the Gaussian surface, I can say that EDS is Q in by epsilon naught, and ds is nothing but 4 pi r square integral of that. So 4 pi r square, and what is Q in? Q in is basically whatever charge we had, let us say Q of this yoke. So that will be Q by epsilon naught. And
Yeah.
E, this is for outside point. Okay. So this will give me E is equal to 1 by 4 pi epsilon naught Q by R square. So you can see this is just like point charge and thin shell. There is no difference as far as outside point is concerned. It is exactly identical to a thin shell or even a point charge. Can you see the comparison?
Yes.
So here you will find that E equals 1 by 4 pi epsilon naught Q by R square. It is just like a point charge. But obviously things will be different when I go inside, because if I take a Gaussian surface, if I take a point that I want to calculate, let's say point R, point M, and I want to find the field here, then definitely the field is going to be, radial. The direction is going to be same because of the spherical shape of this thing. So definitely the field is going to be radial like before, but that value might change. This is your E at P, this is your E at M. Now what I'm going to do is I'm just going to take another Gaussian surface. In this case, I will take a different one. I'll probably take one that passes through the point M. That's all. That's what I have to do. There is no other option. So when
Yeah.
this essay it passes like this, So this distance is small r, and in that case I'm writing in black there. This distance is also small r, but that is for outside point. This is for inside point. So this is small r, this, from the center to the point M. In this case, from the center to the point P, both are different. So derivation is also done separately. So for inside point, I can say, I can again apply Gauss law. I'll say that integral of E dot ds is equal to q in by epsilon naught. Everything will go like everything is same, like before, but only thing we'll have here is, we can say that this is E into 4 pi r square by the same logic that we applied earlier also. But E q in will change, right? Q in is going to change now because Q in is basically the charge that is contained within this blue region. Okay.
Yes.
So that will not be the whole yellow thing. We can already see. So definitely that will be a part of that. So here we can calculate Q in. We can say that Q in equals whole charge multiplied by the fraction of volume that is covered. Fraction of volume means volume that is inside the blue thing is 4 by 3 pi r cube, whereas volume of the whole thing is 4 by 3 pi, let's say capital R cube, where capital R is the radius of the charged sphere itself, the yellow thing.
Yeah.
So definitely the whole charge is not there, only proportionally we have to, let's say half the volume is covered, then charge also becomes half. 1/3 means 1/3. Whatever be the percentage, same thing will be there. So we can basically write this as Q in equal to Q into R cubed by capital R. Right?
Yeah.
So that's very important here, this result. We'll emphasize this, that here Q in changes, that's why the formula is supposed to change. So when I write the formula further, so I'm running out of space here. We'll just move on to the next whiteboard now. Okay. So here,
okay, fine.
Have you followed till here?
Yes, sir. Followed.
So E to 4 pi square is Q in by epsilon naught. So what I'm going to write, maybe here, let me write. So that means E into 4 pi r square equal to Q in is Q r cube by r cube. So that means E will be 1 by 4 pi epsilon naught is also there, right? So that will be epsilon naught also here. Okay, this is really this is a tight squeeze. Just a second. Yeah.
Yeah.
So what I'm going to do here is this epsilon naught is also there. So I'll say 1 by 4 pi epsilon naught Q in, and r square gets cancelled, so only r is left by r. This is the final expression.
Got it.
It's very much different from the previous case, right? So you can note this down, and then we'll discuss graphically how we can draw the graphs of this. So this is E inside, and this is E outside.
Yes, sir.
Okay. In the next part, what we're going to do is we're just going to write down this formula and see what graphically they mean. So graph between electric field and R. We're going to draw E versus R for a solid sphere. So if we draw the graph on the x-axis, I'm going to take the distance from the center, which is small r. And it starts from 0, it might reach the radius of the charged sphere, and then it can go on till infinity. And on the y-axis, you'll have the magnitude of the electric field. So you can see formula E in is equal to 1 by 4 pi epsilon naught q by qr by r cube. And E out will be 1 by 4 pi epsilon naught q by r square. So here you can see initially inside the field will go linearly. Can you see? It's just something like y equal to mx.
Yeah.
So it's something like this. But on the other hand, next it will be going by the inverse square law. So then it will go like this. This is the graph for a uniformly charged sphere. Okay. And on the other hand, for a thin sphere, spherical shell, or even we can say for a conducting sphere, because in conductor always the charge is on the surface itself. That acts very much like a thin sphere only. Both will have same uh, variation of field. So here again I'm doing the same thing. E versus R I'm drawing. E on the y-axis, R on the x-axis, and you can see the formula is going to be E in is 0, whereas E out will be same like point charge 1 by 4 pi epsilon naught q by r square. This we did in the previous class. So here I'll assume that this is capital R. So I'll just draw the graph, which will be till here it will be 0, and then all of a sudden, you know, it jumps up to a certain value, and then it drops down from that value. So what is this value? We might ask. So this is the electric field at the surface, which is 1 by 4 pi epsilon naught q by capital R square. Similarly here also 1 by 4 pi epsilon naught q by capital R square. So I hope you got that. You can note it down.
Yeah. I have to remember this, like.
Well, not necessarily, I mean,
Okay. Basically, just understand and keep it.
Formula you should remember, right?
Okay.
Formula
Yeah.
then anyway you can draw. It's not a big deal to draw the graph, but you should know the formula.
Okay. Cash. Sorry, just a minute, sir.
Yeah.
My dog is actually snoring.
Okay. Let him snore. No, it's fine.
Okay.
You want to wake him up or what?
No. He's literally stuffed his snout to the side of the wall, like almost like it's stuck.
Okay, yeah. Yeah.
Okay.
Okay, next thing. You drew it or what?
Yes, I do. I'm just writing down the formula.
Cool.
Yes, sir.
Okay. So now we'll take a 10-minute break here and we'll carry on with the rest of the Gauss law and the
Okay.
questions related to that. Fine?
Okay, fine.
Cool.
Yeah.
Hello.
Hello?
Yeah, Ananya, shall we continue?
Yeah.
Okay. So now I'm going to talk about a couple more applications of Gauss law. One is the electric field due to a line charge. Okay. So electric field due to an infinitely long line charge or charged wire. It could be. Basically, this is a wire. Okay. It's very long. So in this wire, you can see that there is charge on it. This is a wire. This is supposed to be very long, as in goes up till infinity, goes down till infinity. We want to find the electric field for this particular wire because of this wire. We are also assuming here that it is charged everywhere. Let's say it has positive charge on it. So if it has positive charge, then the field will be, let's say at any random point P I'm taking, and the field will be outwards like this. If it's a negative charge, then of course the field will be inwards. We are already aware that field is outwards for positive and inwards for negative. So here,
Yes.
the Gaussian surface that I'm going to assume is a cylinder.
Mm-hmm.
There's a reason why I do that, because for a linear charge, cylinder is symmetrical and not sphere, right? You can imagine that. This is the sort of cylinder that I'm assuming here.
Yeah, got it.
Passes to the point P, more or less. This is it. Okay. So here, few things to note here. One thing is electric field will be outwards everywhere. So here also it's outward, but you can see that it is not crossing the flat surface at the top and bottom of the cylinder. So it will not contribute anything to the, what shall we say, to the flux, the electric flux. Okay. So here the
Yeah.
electric flux due to the flat surface is zero, only the curved surface is what the contribution of flux comes from. So curved surface, if I write Gauss law for this Gaussian surface, the green one, I can
Yes.
say by Gauss law, again I'll say E dot ds equal to q in by epsilon naught. And here E dot ds becomes simply EDS, because again the field is always parallel to the area vector, and that is equal to q in. Now q in is the interesting part. Here let me assume that this Gaussian surface is having a total length of L. I've just assumed this. It's not given in the, it will not be given in the problem. We have to assume some length L of this, and then lambda will be given. Okay. Like I discussed continuous charges with you, continuous charge distribution, then lambda was the linear charge density. So here obviously this is a line charge, so we'll have to consider only linear charge density. So when we do that, we say that integral of EDS is equal to q in by epsilon naught, and that will be exactly q in. If this whole thing is L, I know that line charge density lambda is given by charge by length. So if I say q is equal to lambda L, that will also not be wrong, right? If lambda is defined as charge per unit length, then
Yes.
charge can be written, yes.
Yeah, Q. Yeah, right.
So here inside, only this L length of the conductor is present, so it will contribute only lambda into L charge. We'll have this formula. Now again, E being constant goes outside, and we are only left with EDS, and that means E into, now formula for curved surface is 2 pi r L of a cylinder. So this will be lambda L by epsilon naught. So E simply becomes, you can see L and L cancels, which is good because we only assumed that thing. So it should have
Yeah.
cancelled. 2 pi epsilon naught R. This is the formula for a line charge, and this is the derivation also if required. So is it clear what we did here?
I understood.
Okay, good. So you may note this down, then we'll move on to the next one.
Fine. Yes, sir.
Okay. Uh, so only last part is remaining now. Okay. Last part is we'll discuss about sheet, a plain sheet of charge. Right. So let's see what we have to do there.
Mm-hmm.
So in plain sheet, electric field, you can see that Gauss law is applied everywhere. So it's very important law. Electric field due to an infinitely large, infinite charged plane sheet.
Okay.
Now, sheet is obviously something like a paper sheet, you could think like that. And I'm just giving it a little bit of thickness. But in reality, there is no real thickness to this. It's a very thin sheet. Important part is that it is very large in terms of the size. It is infinitely extending in all directions. But obviously, for drawing purposes, we have to take some finite section so that we can at least see it. This is just a section of the sheet that I have drawn, and I'm going to go ahead and discuss Gauss law for this, what to apply. So first things first, we'll take a Gaussian surface. Now here you could take the Gaussian surface to be a cuboidal surface, or you could even take, your cylinder, whichever is more comfortable. So let me take cylinder as we already took previously also.
Okay. Oh, the diagrams come out very well.
Sorry.
The diagrams come out well.
Oh, no, I'm used to this. That's why. You'll also, be able to draw very comfortably once you do it once or twice. So this is the
Yeah.
sheet, and I'm taking this Gaussian surface. which I'm assuming you can see here that it intersects this thing at this spot. So I'm going to say that this is the cross section where the plane surface intersects or interacts, you could even say that, with this Gaussian surface. I'm just going to draw this with a dashed line, and this is the region where the charge actually is there, right? Because you know here the whole sheet is charged. There is positive charge, let us say, on the sheet. Obviously, again, for negative, you have to take just opposite direction. Same thing, everything else. But here, the charge inside this area will be Q in. That will be equal to sigma into A, where A is the area of this shaded region. And sigma, just like continuous charge distribution we discussed, sigma is nothing but charge per unit area. So I can say charge is equal to sigma into A. So that's what I have written here also. And now here area A is this, which is the same as the area of this region as well as this region. So we could have taken R and said area is pi r square, but it's even more convenient if we just take A, some area A, because it's going to cancel anyway. So we'll just take A. Now what is going to happen is I'm going to assume my point obviously lies here. That's why I'm taking it like this. So you can see that if I apply Gauss law, this is the point where I'm trying to calculate the electric field. So if I again apply Gauss law, E dot ds is Qn by epsilon naught. And again, you can see that in this case now, the curved surface does not contribute anything to the flux, as the field is always parallel to that thing. So only thing that contributes is the flat surface, as opposed to the previous case where the curved surface was the only one contributing and flat surface did not. But here I can say that E is always parallel to the area vector here also, and on the other side again the field will be away from the sheet, so it will be towards the left on that side, and again the area vector ends up being in this direction for this one also. As I said, area vector will be outwards. Okay, direction of area vector will be towards the outer side. So not inwards. Here it will be towards right. Here it will be towards left. You can see that electric field and area vector are parallel in both the surfaces. So definitely I could say E dot ds is nothing but EDS. And again, E is constant because this is a symmetric surface. It's a very large sheet, so it doesn't matter if you move a little bit here and there. So EDS, that's why we take infinite, you know, because this motion should not matter so much. If I'm moving from point P to, let's say, this point, it should not matter, which only happens for a very large surface. So Q in by epsilon naught. Now ds can be simply integrated to give you the flat surface area, and flat surface area, you can see here there are two areas which are contributing. One is pi r square here, which is A, and one is pi r square here, which is A. Can you see? There are now two surfaces which contribute to the flux. So I will say 2A, not just A, but 2A. And Qn is simply once, sigma into A, right? If this was a thick sheet, then sigma on one side and sigma on the other side. But here this sheet is paper thin, okay? It's really thin, almost zero thickness. That means only one surface of charge is there. So only sigma into A will come. If this was a thick sheet, which is not part of CBSE syllabus, but for competitive, you may know that this will be 2 sigma A if this is a thick sheet. So sigma A by epsilon naught. So E will be simply, A and A will again cancel, which is a good thing because it is something we assumed, and then rest is given sigma by 2 epsilon naught. Sigma will be given to us and epsilon naught is anywhere constant. So that's all. You just need the value of sigma to find the field of a plane sheet. These derivations I am doing because they are very important from CBSE perspective. They may not directly ask the formula, but definitely you should know all these derivations that we have done, starting from first one.
Yes, sir.
Cool.
I'll note this down.
Yes, yes, please. just a second, Ananya. Carry on. I'll be right back.
Okay, sure. Hello?
Hello.
Hello?
Yeah, Ananya. Sorry about that. Somebody just
No
came.
problem.
Yeah. So let's just carry on our discussion.
Yes.
So I hope you have written all this down and you
Yes,
understood.
I did.
Just rewind and see that we have done it for few things today and few things we did yesterday also, right? So now next part obviously becomes example 1.13, which is really another application. And I just need you to read it and I'll help you out with this, how we'll solve it. This is again an application of Gauss law. And this gives us an idea that new kind of questions may also come in CBSE exam and we might have to attempt them. This is really a typical part of this chapter, the most
Got
important.
it.
Yes. Please read it, how the charge distribution is, what to do, and let me know whenever you need any help on this. We'll try to solve this step by step.
Got it. Hello?
Yes. Tell me.
Yes.
Did you read the question?
Question?
Yeah. Did you read the question?
No. I was just revising what all I wrote.
Oh, now you're supposed to do 1.13, no? you go
Oh,
that detail.
okay.
Please.
Okay. Oh,
Revision.
probably I didn't hear you. Sorry.
Okay.
Yeah, I was like revising all the concepts that I just wrote because, like,
It's okay. That is also good. If you revise for 2 minutes, that's a good thing. Now just try to attempt question number 1.13 example on page number 40. That's again another application of Gauss law. And these kind of questions may pop up in the CBSE final exam. And then you have to just think at that moment what to do. So this will be a good exercise in that. Yes. Here again we'll apply Gauss law. So maybe you can try along those lines.
I don't seem to get it.
See, we have done for the sphere today only, right?
Yeah.
Now, if you read it, you can see that this is also like a charged sphere, firstly, but there is also some other part of this. Okay, so for example, this is essentially the sphere in which this negative charge lies, the atoms model that we are discussing, right? Now, if you think about it, if you take another region, right, like here we have taken the negative one. Now, if you take at the center another region, okay, let's say this one. This is the positively charged nucleus, right? This is the positively charged nucleus which they are discussing. You can see in the diagram, figure 1.32. Can you see?
Yes.
That is having a plus Q charge. So positive charge here, and rest of the region all negative.
Yes. Right.
So now they're asking for two places. One is R smaller than capital R and the other one is R greater than capital R. This capital R is basically the radius of this negatively charged yellow sphere. And you want to find essentially the electric field in two regions. One being at a distance of small r greater than capital R, which is outside point, and the other one being a region small r smaller than capital R. So these one is internal point and other one is external point. So I'm just going to label them separately. This is point P and this is point M. This is outside point, this is inside. Now obviously I have to assume that my Gaussian surfaces. For the outside one, where should I take and what kind of surface do you think would be suitable?
For the outside one.
Yeah, what kind of Gaussian surface do you think should be suitable?
No, no, 1 second.
Because for the spherical case earlier, which shows, you can check back in your notes.
Like it's a sphere itself, so
yeah. So for sphere, we go for a sphere only because that's the most symmetrical thing we can get, right? In case of a spherical charge.
Oh, the egg.
Yeah, the egg is a sphere, so the Gaussian surface should also be a sphere, right? Because the egg represents the charge distribution, and the shape of charge distribution.
More simple.
Sorry.
No, sphere will be like the most simple one.
Yeah. So always sphere is not the best option because the shape of the charge distribution matters. So if it's a point charge or a spherical charge, then you have to go for a sphere itself. If it's a plane sheet, you go for a cylinder. If First
Yeah.
the line charge, then also you go for a cylinder, right?
Okay.
So
Yeah.
here definitely I'll take a Gaussian surface which is spherical in shape and passes through the point P. Though, and also it should be centered around the center of the charge distribution
Got it.
because of symmetry. So now I can apply the same arguments that I've been applying till now. So EDS will be Q in by epsilon naught. Only here it is very small, okay, because outside point, I'll say E out into 4 pi r square is Q in. Q in is how much here? According to the question, can you read the question and let me know? What is the
Yes.
magnitude of charge inside this sphere, the blue sphere that we have chosen the Gaussian surface?
The small one inside. Small r.
No, I'm talking about the smaller outside one. We are doing for the outside one right now. Okay?
Yeah.
Yes.
How do like formula? If I'm in the formula, you're asking?
No, I'm just asking how much charge is inside this blue
Okay.
sphere. You need to read the question to give me the correct answer for this.
ZE.
That's the. Read it properly, will you?
Okay. An early model of an atom considered it to have a positively charged point nucleus of charge Z, surrounded by a uniform density of negative charge up to radius r. The atom as a whole is neutral. For this model, what is the electric field at a distance r from the nucleus?
So, I think you already read that part where the net charge is given. Which one is that part?
Net charge.
Ananya, you just read the atom as a whole is neutral. It's written in the
Yes.
question. So,
Zero.
good. Amazing, you're a genius. So, E out will be
No,
zero.
not at all. Why did I think so much on that?
I don't know. You should have thought, maybe you should concentrate more in these kind of questions.
Yeah.
They demand attention. Lot of attention. So that's for an inside point. That's just child's play because the right hand side becomes zero. So I just said E out should also be zero in that case. And then comes the inner one.
Yeah.
The real one. Okay. Here we need to find what is the electric field inside at a point inside. So E in.
Yes.
Again, I'm gonna do dot ds is equal to q in by epsilon naught and same thing. So that will be E in into 4 pi r square equal to q in by epsilon naught. Now I need your help that what will be the value of q in this case for the second one, the smaller blue sphere.
Okay, that is ZE.
ZE is the positive charge and there is some negative charge also because you can see this negative one is
Yes.
also there. So how much
Oh,
negative?
Negative is also the. How do I consider that as well? Like.
So they are saying surrounded by uniform charge density of negative charge. This is uniform charge from 0 to small r, like we did here also.
Yeah.
What did we do here?
In this one.
We said charge inside is equal to Q by R cube by dividing the volume. So here also we'll do the same thing.
Okay.
So ZE is already there and minus ZE is also there, but not all of the minus ZE. Only till distance small r. So I'll say R cube by R cube.
Okay.
And then I say that E in finally.
Okay.
Then E in will be ZE 4 pi epsilon. Obviously, this whole thing is divided by epsilon naught here. and we'll say 4 pi epsilon naught, and then 1 by r square minus r by r cube. This is your final expression.
Got it.
Okay, great. I was sort of hoping, secretly, I was wishing that you will actually do this yourself, but I think we are too early into the into the course to expect that kind of thing. Never mind.
Yeah.
At least
No,
we
like
got
the
it.
theory part we just finished, so maybe after
Yeah,
like two,
that's what,
three questions, I'll get an
yeah,
idea.
yeah, yeah. That's what I mean. That's what I'm saying. That after a while, you'll be better off in terms of solving questions yourself. So, how much exercise have you done till now?
So until the 12th one, basically, and 14th one we solved
Just
it
give me a
now.
moment. Just. A
Yeah, sure. In the right, in the right, in something that I'm not good Okay. Inner questions. To infinitely appreciate E dot S is given by epsilon naught. And then is equal to by A. So got it. Line charge cylinder. So by E ds equals given by epsilon naught. Phi E ds equals lambda L by epsilon naught.
Yeah, no. So let us carry
Yes.
on. So we have, I believe, finished all the examples, and
Yes.
also apart from that, you have done most of the exercise questions, is what you told me. Till which question you tried?
So
14.
12 basically.
Oh, 13, 14 also we discussed though. So now we can start from 15 and go
Yes.
all the way to 24. Okay. So
Yes.
additional also we will do, because here the additional questions are not that difficult, and also they are important from CBSE perspective. So we'll actually
Okay.
be teaching the additional also here, but let's just start with the regular ones. So I want you to be a little fast, because this is
Yes.
class time when we are attempting. So try to be focused, try to be sure about what you're doing, and ask me whenever you need
Yes.
any help. Please, I'm here only, right? So let me know. You can start with 15th question.
15th one. Okay, fine.
Yes, yes. So you have to draw one by one. Here they are giving us some textual information. We need to convert that into graphical information by drawing.
Yes.
So just use your imagination a little and let me know what you think of it.
So what I didn't get is here.
Hmm.
They say whose plane is parallel to the YZ plane.
Yeah, so plane, see, basically they are asking on a side whose plane is parallel to the YZ plane in a square of 10 centimeter. So side, what side we are talking about? Let's say there is a square. Okay.
Yeah.
This is the square that is in question, and it is saying that uh, through a square of side 10 centimeter on a side, whose plane is no side is not parallel. They're saying plane is parallel to YZ plane. So definitely, this is the y-axis. Let us suppose, or let us say this is the z-axis. Then this will be your y-axis. I mean, either of them. One could be y, other could be z. It has to lie in the YZ plane.
Yeah, got it. So I didn't understand. Okay, so basically they're asking flux of the field through the square.
Yeah.
And the one side of the square, fine.
Yeah.
So what do they mean through the square? Like I didn't get which formula to use.
Flux is directly you need to find E dot delta S, where delta is the
okay. Sorry, you were saying?
Where delta is the area vector. That is
yeah.
area magnitude into direction. So
Got it.
you know what to do there probably. If you have revised, right, the notes.
Yes.
Okay.
Now I missed that. So 5 will be E into. Okay, I'll tell you the final answer.
Yeah, please.
Okay. So it's 30 Newton meter square per coulomb.
How do you get 30? You should have gotten 0.3 because side is 10 centimeters. So 0.1 into 0.1. I'm wrong. Yeah, I'm wrong. You are right. Correct. So very good. Let's do part B now.
Okay. Since normal to the okay. Now alright. Normal to the plane makes a 60-degree angle with x-axis. The same thing with theta equals 60 degrees.
Yeah,
like
correct.
A cos theta.
Yes. So we'll do cos 60 here, which is half, basically.
Yeah.
So this was the simplest question in Gauss law in electric flux you could get. This is just beginning.
Very simple.
Yeah. Now we'll move on to 1.16.
Yes. What is the net flux of the uniform electric field of exercise 1.15? Oh, the same question. Okay. Net flux of the uniform electric field here through a cube of side 20 centimeter oriented so its faces are parallel to the coordinate planes.
Coordinate planes means x, y, z. So basically all these three sides will be along x, y, and z axis.
Yeah. So if it's parallel, then all three surfaces.
Yeah. So you can draw it actually.
Okay. How do I draw this?
Cube.
Oh, I remember the diagram. Yeah.
How do you draw a cube? You can just try like that.
Yeah. I remember this.
So roughly, I'm just gonna give you an indication here on the board. Take a
Draw it.
square, then like this, you have to sort of. This is what.
Yeah. Got it.
You know how to do this, right? Two squares
Yeah.
and.
No. I meant like with the axis.
Oh.
So basically, okay, cube of side 20 centimeter. Fine. Oriented so its faces up. Faces are parallel to the coordinate axis.
So this plane, these two faces are parallel.
So all faces are parallel then, right?
Yeah. To what? To different planes, not x-axis, not the electric field.
No, not particular. Like all faces are parallel to all the like coordinate axes.
No, all faces are parallel to some of the coordinate axes. Is what you can say. How can all the faces be parallel to all the coordinates? That's not possible.
No. Sorry, not all. I mean,
some.
Sorry.
Some. Yeah, I got your point. I understood what you're trying to say. Yeah. Okay.
So when they parallel, 1 second, there will be 0 then.
No. How?
1 second, sir. See, because when they're all parallel, so field lines enter and then they leave. Like number of field lines which enters, all of those will leave.
You are correct. Okay, but how will you write it? How will you calculate the flux? You have to show positive for one side, negative for the other. You remember we did this in those examples.
Yes, I remember.
So
Yeah.
you just do it on the notebook and let me know when you're done, because it's important that you write it. If you say whatever enters leaves, that is correct for 1 mark, maximum 2 marks. But if this question
I understood the concept, but I have to put it in right words in the paper.
You have to put it in math. Yes.
Yes.
So essentially you are correct, but you need to write it.
Okay.
Yeah.
So I'm not exactly getting it. I'm supposed to use the formula phi equals like E dot delta
See, these 4 faces, you can say they are useless. Okay, because net flux will be 0. But yeah, definitely this one here, it will be positive E into delta A, whatever A square, A being the side, and here it will be minus E into A square, because here n cap is in this direction, whereas electric field is in the positive x direction, and here n cap is also in the positive x direction, and electric field is always in this question in the positive x direction, because here they have given the field 3 into 10 to the power 3 I cap, that is electric field is in the positive x direction with the magnitude 3000. So that's why I can say that the left face will have negative flux and the right face will have positive flux, equal and opposite. So they will cancel out to give 0, and all 4 other faces will anyway be 0. So total will be 0 itself.
Okay, minus. Okay, that's how I should represent.
Yes.
All right. I'll just write it down properly.
Sure, please.
Got it, sir. Done.
Okay. Let's move on to the next problem now.
Careful measurement of the electric field at the surface of a black box indicate the net outward flux through the surface of the box is this. Okay. What is the net charge inside the box? Is the net outward flux through the surface of the box when zero? Could you conclude that no charge is inside the box? Why or why not? Okay.
So go one by one. Part A first. Part B.
So net outward flux through the box is given, that is 8 into 10 power 3. Okay. Net charge inside the box. So phi is equal to Q in divided by epsilon naught.
Correct.
So Q will be phi into epsilon naught. Right. So I'll put the Q is given in epsilon naught value. I'll put 8.85 into I don't remember. Sorry.
10 to the power minus 12. Okay.
Minus 12. Okay, fine. 8.85 into 10 power minus 12. 1 second, just do it. Into 8 into 10 power 3. So 10 to the power minus 9. 5 is a 44 carry. 64 plus 48, 6 carry. 70. So 70.8 into 10 to the power minus 9 I got. That will be 7.08 into 10 to the power minus 8. So, okay. So, part A is done. Now, part B, net outward flux through the surface of the box were 0. Then, would you conclude that there were no charges inside the box? So 1 second.
Yeah.
Net outward flux through the surface of the box were 0. Then so could you explain this to me? The B part of the question.
What do you think the answer should be firstly? So they are saying that suppose the net flux is 0. Then how much charge do you think inside should be there?
So see, if net flux is 0, then it can either it can be 0 inside or no. If positive. What if it has like positive and negative charges equally?
Yeah, correct. So that is the case. We can't really conclude that the net flux is 0 because net charge is 0. So we can say Yeah, net charge is 0, but we can't say that both may or may not be
Yeah.
present. That is the case. So we can't say that charge is not there at all. Okay. So
Yeah.
that is, we can't conclude, as it might have equal positive as well as negative charges. So you are correct. Very good. You're doing well.
Okay.
Now let's look at
Thank
the last question for today, 1.18, because that's a little
Okay.
typical. So I want you to do it with me itself. So please
Okay, sir.
read it up. Yeah.
A point charge of 10 mu, okay, is a distance, is at a distance 5 centimeter directly above the center of a square of side 10 centimeter. What is the magnitude of the electric flux through the square? Hint. Face of a cube with edge 10 centimeter. Oh, they shouldn't have given this hint. That is, okay. What is the magnitude of the electric flux through the square? Oh. Come on, I can do this. Mm. This is kind of tricky. So just give me 1 minute to think about it.
Yeah.
No, so could you help?
Sure. So see that hint they already gave, right? And according to that, we have to think now. So here we want to find the flux through this, and this is anyway very typical. So I'm not assuming that any student would get it in the first go. So don't worry. Yeah. So here I'm going to assume.
I don't understand this, sir. They
Sorry.
are saying we should consider it as one face of a cube, right?
Yeah. So
No,
I'll tell you
but
the
then
reason.
electric flux will be there in the whole thing then.
Yeah. So we'll divide it by 6 then.
Oh no! Oh yes, yes, yes. Yeah, I could have got it.
Yeah.
Oh.
See,
Okay.
you almost got it, but anyway, you divide the whole thing by 6. Q in by epsilon naught by 6, and that will be your answer, right?
Oh yeah.
It's okay. So anyway, we'll stop here, and your homework would be to finish from 19 to 24 if you have time. If you don't have, anyway, we will finish in the next class. Okay.
So I don't think so.
Uh-huh.
Yeah, because I'm writing the practicals and I have
Yeah,
chemistry class also today.
it's fine. You know what? We'll just do the questions in the next class. It's okay.
Yeah. No, like, so in the sense, if I get time, I'll definitely do, because writing practicals continuously. So it's
Leave
like,
it, leave it. Don't do it, I'll say. Just
yeah,
don't even
in
consider,
between.
because you need some break also. You don't have to work like a donkey or something. Okay.
Yeah.
Yeah. Be a human, being human, and I'll see you next time. Okay.
Yes.
Bye.
Thank you, sir.
You're
Good night.
welcome. Good night. Yeah.